Jai Hind everyone, I am Shruti Jain, Assistant Professor, MCA Department, Ajay Kumar Garg, Engineering College, Ghaziabad. The topic that we are going to discuss today is about memory management. This is under the subject operating system. The subject code is KCA 203 and the target students over here are MCA first year students, second semester. So understanding what memory management is basically, so we know that a program must be brought into the memory and it is placed within a process for it to be run. So for that we need to have some queues in which the jobs that are coming into the system are to be placed. So input queue or the job queue, these are a collection of processes on the disk that are waiting to be brought into the memory to run the program. Now, when the user program enters into the system, it goes through several steps before being run. So, memory management basically refers to the process by which a computer's operating system handles and organizes its primary memory. So, it involves tracking each byte of the system memory and deciding how to allocate them to meet the system requirements. So, for that we have some of the memory management functions. The first function talks about keeping the track of the status of each location of the primary memory that is either free or allocated by some other process. It also determines the allocation policy for memory, that is to whom it should go, how much, when and where. Allocation technique: once it is decided to allocate the memory, specific locations must be selected and the allocation information must be updated. The deallocation technique and the policy handling the deallocation of memory. After deallocation, the status information is also to be updated so that later on when any other process enters into the system, that memory is given to that the upcoming process. So we have different memory allocation methods. The first one is contiguous memory allocation, in which we have the single process and the multiple process contiguous allocation method. In multiple processes, because multiple processes are entering into the system, for that we have fixed partition allocation and variable sized partition allocation. When we are talking about non-contiguous memory allocation, that means the process that is entering into the system is not saved in the continuous memory. So for that we have the paging, segmentation, or the combination of paging and segmentation. So starting with the first one, what basically is the contiguous memory allocation? Contiguous memory allocation, first of all, when the memory is when we talk about the whole of the memory, it is divided into two parts, that is two partitions. Partitions is basically splitting the memory into different sections. They can be equal or unequal depending upon the type of allocation that we are doing. So main memory is divided into two partitions. The first one is the partition where the operating system resides in the low memory with the interrupt vector, and the other partition is for user processes that are held in the high memory. So coming to the fixed sized partition, that is a static partition. That means that the partitions are done in the beginning itself. When the process enters, the partitions do not change. So there the partition contains exactly one process and the degree of multiprogramming is bound by a number of partitions, and hence it is also known as multi-partition system. Now when a partition is free, a process is selected from the input queue and it is loaded into the free partition. When the process terminates, the partition becomes available for another process and the process goes on. So this method is basically used in batch processing operating system, where the operating system keeps a table indicating which part of memory are available and which are occupied. So in the fixed partition also we have two types of partitions. The first one is equal sized partition and the other one is unequal sized partition. The equal sized partition is like this, wherein the process of whatever size enters into the system, that process is allocated this much of partition. The process size should be either less or equal to the size of the equal partition that we are having. If the size increases from the partition size in the fixed one, then in that case the process is not allocated that particular partition. Now here it also accommodates the partition which is of very small size. If suppose we have a process of 2 MB also that is entering into the system, so this 2 MB will be taken up by the process and this 6 MB would be free. So that leads to the wastage of memory. So for that we had another option of unequal sized partition, where we have different partitions which are of different sizes. So depending upon the process that is entering into the system, the partitions are allocated to those processes. So one benefit of it is we have a process which is of more than 8 MB size can accommodate this partition, which was not possible while we were talking about the equal sized partitions. But when we are talking about this, as we have just discussed, in case a 2 MB process enters into the system, in that case, a lot of memory, that is of 6 MB memory, is wasted, which cannot be allocated to another process. So those consequences are termed under two categories. The first one is internal fragmentation and the other one is external fragmentation. So coming to the internal fragmentation, it says that if the size of a process is less than the total size of the partition, then some sizes of the partition, they get wasted or they remain unused. We have unused partitions in that. So which leads to the wastage of memory, and this is known as the internal fragmentation. So in case if we talk about this here, this wastage of 6 MB is basically the internal partition. Now coming to the external fragmentation, the total unused space of various partitions, they cannot be used to load the process even though we have some space available, but it is not in the contiguous memory. So if we look over here, this is an example of internal fragmentation and external fragmentation. So we had the equal sized partitions of 4 MB wherein all the processes that entered into the system were of the size 3 MB. Now when these processes entered in the memory, there was an internal fragmentation where this 1 MB space was unused and it was left when the 3 MB process entered into the memory. Now this 1 MB was combined together and it was made into a block, but still then also we could not use this unused space because we had these not in the contiguous memory location. So this is what it is showing in the example. The remaining 1 MB space of each partition cannot be used as a unit to store a 4 MB process, even though we had sufficient space available to load the process, but still the process will not be loaded in that case. So here we have a process 5 which is waiting for the memory allocation, though we had this 1 MB of free 4 MB of free space, but we cannot allocate that memory to the process 5. So that was all related to dynamic storage allocation method, where we had seen that there were chances of more of internal fragmentation and external fragmentation. So we had another concept where we are dynamically storing we are dynamically partitioning the memory. So in that case, let's take an example where we have a block of memory available and the operating system is residing at the top containing the 8 MB of memory space. Now the process P1 entered into the system and it wanted the memory because we had free memory. This process 1 was allocated the 20 MB of space, leaving behind the 36 MB of space. Then the process 2 came with 14 MB of space and then we were left with 22 MB, and process 3 came with 18 MB of space. Now because we do not have enough memory to load the process, so suppose process 4 came up which was maybe of a higher priority. So in that case, this process 2 was swapped out of the memory. Swapping out means it was taken out of the memory, and we had the 14 MB of space left where the process 4 entered of 8 MB, and this 6 MB was the unused space. Now another process, the process P1 suppose got executed, so it was swapped out of the system. We had the 20 MB of space over here. Now the process P2 swapped in, it was loaded again into the system, and hence we had the 14 MB of process P2 loaded into the space where the P1 was there, and we were left with 6 MB of space here. So we have 6 MB and 4 MB of unused space. So this is the internal fragmentation, wherein the processes had some unused spaces at different parts and not in the contiguous memory allocation. So this also led to the fragmentation concept. So the solution of that fragmentation is compaction, wherein that external fragmentation can be, the blocks of external fragmentation can be compacted together and we can have one block of memory which could be given to another process that is entering into the system. So for that, From time to time, the operating system shifts the processes so that they are contiguous and so that all the free memory is together in one block. In general, at any given time, we have set of holes of various sizes which are scattered throughout the memory. So when the process arrives and need the memory, the system searches for the set of holes. Holes means the free partitions that is large enough for that process. If the hole is too large, it splits into two parts. One part is allocated and the other is returned to the set of holes. Now we have some of the techniques or the algorithms how we allot these processes. So we have three algorithms. The first one is the first fit, best fit and worst fit. The first fit algorithm says it allocates the first hole to the process which is big enough. As soon as a process comes, the first hole that is available for the process. Suppose here we have, this was a memory size and a process which was coming into the system this was the last one. Now a process came which needed some memory space which was less than 22 KB. So this was allocated into the first fit. The memory size which the process needed is allocated the first one. The best fit, it allocates the smallest hole that is big enough. So here it produces very small leftover holes. So if we talk about the smallest fit, it was a 14 KB of process. So this was allocated when it was talking about the first fit, but when we talk about the best choice or the best fit, there this would be the best possible place where the 14 KB process can be allocated. Now if we talk about the worst fit, in that it talks about the largest hole that is available and allocates it to the process, whether the process is that much big enough or it is a very small process, but that process is allocated the largest hole. So in that case, if we look over here, the 14 MB space would be provided to this 36 KB instead of the first fit and best fit. So in that case, we have seen that the first fit and the best fit are better than the worst fit in terms of speed and storage utilization, because here we have very large holes created which could not be used maybe further on. So for that, we have one more algorithm, that is a next fit algorithm, which talks about the first hole from the last placement. So if we talk about these two figures, here the last allocated block was 14 KB over here. Now the next process that is coming, that is again of the 14 KB. Now that process will be start looking from here and would check for the place which is 14, where we have the 14 KB or maybe 14 or 16 KB of space left. So in that case, it would be talking about this one where the 16 KB process is entering into the system or wanted the memory space. So coming to advantages and disadvantages, for the first fit is the quickest because it does not have to traverse throughout the memory space to identify which memory is to be taken. But it is not optimal because the first memory space could be very large enough in case a very small process enters into a system. Best fit is good, but it is an exhaustive search because you have to go through all the memory management. Then worst fit is again an exhaustive process search where you have to search for the largest available allocation and you might not use up the large holes as effectively as you could. The next concept for non-contiguous memory allocation is paging, where the we have the logical memory, a process that is entering into the memory divided into different pages. We maintain a page table to map these pages into the physical memory. Now it is non-contiguous because in the physical memory these pages are not necessarily stored at the same address location or in the contiguous memory allocation. So in that case, what we have, suppose we have a process which is divided into these 4 pages, page 0, page 1, page 2, page 3. Now these indices talk about the page numbers and this talks about the frame numbers on which these pages lie. So here we look, the page 0 is lying at the frame 1, the page 1 lies at the frame 4, page 2 lies at frame 3 and page 3 lies at the frame 7. So here the CPU generates a logical address where every address is generated by the CPU is divided into 2 parts. The first one is a page number and the second one is a page offset. Now the page number is used as an index to the page table which contains the base address of each page in the physical memory. The page offset, it is combined with the base address to define the physical memory address that is sent to the main memory. Now, it also involves the translation of virtual address into the physical memory. The memory management unit, it converts the logical address into the physical address. The base address plus offset is sent to the main memory unit. So this is the address translation where we have the CPU, the logical address, which has a page number and the page offset. We have the page table maintained where the page numbers are there and the corresponding frame numbers are lying over here. These are through this physical address, and in the physical memory we can identify that page at a particular frame. Coming to segmentation, it is a memory management scheme that supports this user view of memory. So a logical address space, it is a collection of segments where each segment has a name and an offset within the segment. The segment are numbered and are referred to as segment numbers rather than by segment name. Thus, the logical address consists of the two parts, the segment number and the offset. So previously we had the page number and the offset, or the frame numbers or the offset. Here we have the segment numbers. So whenever the user compiles a program, it might create the following segments: the code, global variables, the heap, the stack and the standard C library. So if we look at the user's view of a program, in the logical address space, we have the subroutines, we have the stack. So this program is basically divided into different segments. The segment that is required by the main memory or by the user is loaded into the main memory whenever it is required. So each entry in the segment table has a segment base and the segment limit. The segment base consists of the starting physical address where the segment resides in the memory, whereas the segment limit, it specifies the length of the segment. So here we have the segment and the offset. So when the CPU requires any of the thing, so the segment number is coming up, which talks about the segment table, which has the limit and the base again. If this segment is less than the segment table that we talk about, then it is this base, it's added and the physical memory, it is loaded into the physical memory. Otherwise, a trap or the addressing error occurs up. So a logical address, it consists of two parts, the segment number and the offset number. The segment number is used as an index to the segment table. The offset D of the logical table, it must be between 0 and the segment limit. If it is not, then the trap, we send a trap to the operating system. When an offset is legal, it is added to the segment base to produce the address in the physical memory of the desired byte. So this is the example of the segmentation. So suppose we talk about that the first segment is of it has the thousands bytes of limit, and it is stored at the base address 1400. So at 1400 we will set this segment 0. The next available address would be 2400, that is 1400 plus 2000 plus 1000, that is 2400. Similarly, when the base address is 6300, so segment 1 lies over here with the limit of 4000. So at which the next available would be the 6700.